Hello, my name is Stan Murawski, and I also respond to the moniker of Stosh. And for those of you who may not be familiar with that nickname, that's Polish for Stan and derives from Stanislaus. I'm a systems technologies evangelist in a Microsoft group called IT Infrastructure and Hosting, which is a solutions group focused on high-end enterprise-class computing, generally mostly server kind of stuff. And right now, what that means for me in my life is evangelizing 64-bit Windows and the development of 64-bit applications to run on 64-bit Windows on Itanium computers. So what we're going to go through today in this session is first an overview of 64-bit Windows. What is 64-bit Windows and what distinguishes it from Windows 2000, 32-bit Pentium, etc. After that, I'll spend a few slides discussing what sorts of applications are the right stuff for 64-bit Windows and how those applications can take advantage and be better on 64-bit Windows and on Itanium. From there, I'll move into talking about what is the difference between development for Win32 and for Win64, and get a bit into the Win64 types, the Win64 API, and what it takes to get existing Win32 code 64-bit ready. And I'll go through a little development example where I took one of the platform SDK programs and moved it to 64-bit. Then in the wrap-up, I'll go through a tools roadmap of where we're at with the tools for 64-bit development, with the beta program, and other resources that are available to you in order to get to 64-bit. And then I'll close, of course, with the classic call to action of what can be done to exploit the power of this platform. The part on Win64 types and APIs will be very C programmer oriented. So if there are some members of the audience who are not C, C++, SDK level developers, that's the part where you might not follow along. But the rest of it is pretty general. Anybody who's computer savvy will be able to follow the rest of this talk. So what is 64-bit Windows? 64-bit Windows is simply 64-bit Windows 2000. It's got a feature set that is equivalent to Windows 2000. There's a single code base at Microsoft from which we build Windows 2000 in our daily build cycle that many of you, I'm sure, have heard about. We take that same set of source code and we compile it with a different compiler, link it with a different linker, and produce executables that run on an Intel Itanium processor computer. That's 64-bit Windows. Same feature set. The API, we are calling Win64. I'm a little afraid of calling it Win64, actually, because it's not that different. The Win64 API is the same as the Win32 API, except that all pointers are now 64 bits long instead of being 32 bits long. So we don't have new APIs. We have the same APIs with the pointers stretched. We don't have any. How many went through the Win16 to Win32 transition? It's nowhere near that level of change. We don't have events like the data that was in LParam and WParam being switched and the need to write nasty macros to track that and make compatible code. It's just a pointer stretch. Another very important point is that we do have 32-bit compatibility. A component of Windows 64 called WOW64, Windows on Windows 64, runs Win32 applications. So you can take an existing Win32 x86 binary and it will run. Win16 apps will not run. There is no Win16 support. You can't run your DOS apps. This is goodness. This is goodness. We've got to cut the past in order to move forward. So the legacy that's gone is the 16-bit, and we now have Win32 and Win64 as our two sets. What's different? What's different is very large virtual memory. Who in the room has ever done a virtual ALEC or a MALEC or a global ALEC and gotten back a no? There's no more virtual memory. High-end apps have that issue, and that issue will, for many years henceforth here, go away. You now have, instead of 2 gigabytes available to you, you have 8,184 gigabytes available to your application. So you've got large virtual memory, and you've got the availability of 64-bit integers. So in a single integer, signed or unsigned, you can now count a lot more stuff. Or when you're counting that stuff, you can count it much more quickly because you can do it in a single integer to the C programmer, which becomes a single register to the hardware. And you can do that much more quickly than you can do floating point or deal with multiple registers and register overflow and all of that. In addition, the Itanium processor has a much faster floating point unit, so those applications that are floating point oriented will run much faster on Itanium than they do on Pentium. While I said we have Win32 support, I said you can run Win32 apps. It's Intel Architecture 64. That's the Intel hardware guys' way of saying what this chip is. IA32 is what we call x86. IA64 is Itanium, which is the processors that came out of the Merced project. That's the code that's going to reach the performance potential of Itanium processor computers. So we have 2 distinct changes here, 2 distinct differences. One, we have a 64-bit chip and a 64-bit OS, which gives us the large virtual memory and 64-bit integers. And we also have a new chip architecture called IA64, which is a whole new ballgame with the way the chip runs instructions. It's a new assembler. So once you get to the assembler level, nothing you know from the past is going to be seen. The apps that can take advantage of this are the apps that need that extra headroom those large integers or that large virtual memory gives you. This would be applications that use very large objects, objects larger than 2 gigabytes. Think about video editing, for example. Today, if you want to write video editing software to edit the Star Wars movie, you have to write a lot of complex code to move that movie into and out of memory in segments, 2 minutes maybe. So there's some 2-minute segments in memory, some on disk. You've got to worry about which ones are in, which ones are out. And God forbid the user wants to edit across the boundary between 2 segments. Then it gets really complicated. In an 8 terabyte address space, you can use the file mapping APIs and file map the whole video in the virtual memory. You can just treat the video as a stream of data. Much simpler code, less bugs, and assuming you got enough RAM, better performance. Databases are another class of application that will take advantage of 64-bit Windows. The other class of apps are apps that count a lot of things. If you've got more than 2 to the 32 things, which is not uncommon in statistical analysis, which is not uncommon in the scientific realm, which is not uncommon in modeling, CAD, CAM, etc., then you can get much greater performance through the use of the large registers, and for some of those apps also the large memory. So we've now got a new int type, int64, which says I really want a 64-bit integer. And now, for example, an encryption algorithm that's dealing with more than 32 bits can do that in less registers and therefore run faster through a more efficient algorithm. The other thing that's true, point 4 here, is all of these Itanium machines are very high-end machines. They've all got chipsets that give you high bus bandwidth to memory. They've all got lots of memory. I've not seen a machine with less than a gigabyte of RAM. They've got high I/O bus speeds, high-end disk subsystems, etc. I invite you to come by the Microsoft booth at the trade show this afternoon. I will be there after this talk. And there's an NEC system there with 16 Itanium processors in it that'll carry 64 gigabytes of RAM, and it has 128 PCI slots. So thinking about how much I/O you can put in 128 slots, that's a high-end box. The first app that we are taking to 64-bit is SQL Server. And that NEC box on the floor is running 64-bit Windows, on which is running 64-bit SQL Server, on which is running an application called Terra Server, which is a mapping database, photographs of the surface of the Earth. The next Microsoft app that's going there is Exchange. So SQL Server might be dealing with very large things, large databases. Exchange Server is a class of app that's dealing with very many things, very many users, very many messages. And the Exchange developers feel really constrained by that tiny 2 gigabyte address space they have to work in now. And they're really looking forward to relief from their perspective of that constraint and going to the 8 terabyte address space. So back office servers in general are the class of app that will gain benefit in the Microsoft set of applications from the large virtual and physical memory. But not all apps. So I do want to say that not all apps are going to be faster and better on an Itanium computer. And Microsoft Office is an example of a set of apps where we're going to make sure the 32-bit version runs well in the Windows on Windows 64 support. We're going to run it through the QA cycle, make sure it's good on the platform, but we're not taking that to IA64 in the near term. Okay, with that, let's now look into what's different from the programmer's perspective, specifically now from the C and C++ programmer's perspective. The size model used in 64-bit Windows is called LLP64, or simply P64, which means that by default, your integers, your long data types are still 32-bit integers. It's only pointers that by default go to 64 bits. So if you take your existing code that says int and long and compile it, it's still going to compile and allocate and plan on using 32 bits for ints and longs, but 64 for pointers. If you want a 64-bit int or long, you've got to use a data type where you explicitly ask for the 64-bit integer, which underscore int64 is the prototypical example. We did this because it's goodness for you, the developer. LLP64 as a model gives you maximum compatibility with your existing code, which lets you get your existing code to 64 bits with the least amount of effort. It's the most compatible with the existing code, and it's also the most compatible for Win64, Win32 application interop, because it introduces the least change to data structures. If we would have taken longs, for example, to 64 bits, there would have been many, many more data structures that were changed, expanded by having 64-bit members of those structures. And that would hit compatibility, and that would also produce, in many cases, what people are calling code bloat, in the sense that when you make all those longs, if you made all those longs 64, that structure would get a lot bigger. And in many, many cases, you're not counting anywhere near 2 billion in those longs. So the goal was least change, maximum compatibility, most rapid migration to 64-bit Windows, and the choice, therefore, was only pointers by default go to 64. Otherwise, you must make an explicit election to be 64. There are new types, some of which are specific 32, some of which are specific 64, and some of which are polymorphic. They go to the size of a pointer on the machine. And those are all defined in a new header file named base.tsd.h. So base.tsd.h defines these new types. Examples are dword32, where you're explicitly saying, I know this is, I want this to be, and it will always be 32 bits. Or int64, which is just the inverse. I explicitly want a 64-bit integer. The polymorphic types end with the suffix of underscore PTR. So here I'm saying I want a dword the size of a pointer, which usually would be a place you would point to a dword. And that compiles to 32 bits Win32, and it compiles to 64 bits Win64. I said only pointers by default went to 64 bits. That's not explicitly correct because there are many data types derived from pointer types. So in addition to explicit pointers going to 64 bits, pointer-derived data types like lparam, lresult, hmodule, those kinds of things are going to also go to 64 bits even when you use those exact types in your source code. The next two slides, I have listed the primary types from base.h, base.tsd.h, and said exactly what it is. Take a look at these. This slide has the explicitly sized types. And here are the types that change based upon which platform you compiled for. So in the next couple of slides, I have some general rules to follow in order to migrate your code from Win32 only code to code that goes both ways. We don't want a source fork here. What we want is a single code base that will compile both ways. That's what we are doing internally. That's how we build Windows 2000 today. One source base that compiles both ways. That's what we think you should do with your code. Get it 64-bit clean so it compiles both ways. So some rules, for example. Use uIntPointer, IntPointer, etc. for those types that have to go to the size of a pointer on the platform. And don't make assumptions about the types dword, long, or ulong being able to hold a pointer. And that right there is probably the most prolific error, if you will, that we see in current source code. People have longs and they assume a long can hold a pointer because they assumed, oh yeah, they're both 32 bits, it's okay. Size T is a type you need to use to specify the size of things that come back with a pointer pointing to them. There's a lot of sloppy code out there that doesn't use size T, instead uses int for the size of what you just allocated. However, the size of what you just allocated could now be larger than 2 gigabytes. So size T compiles to a 64-bit entity when you compile it for 64, so it's big enough to hold the size of a virtual alloc of a few terabytes. So you can't make any assumption about the length of a pointer or the length of the thing the pointer points to fitting in to a traditional long or 32-bit int. I said it was a simple pointer stretch of the API set. And I've said that base.tsd defines most of the change. That header file is in the platform SDK that ships today for Windows 2000. The primary issues you run into when you put that header file in your code and you compile it, in a lot of ways comes down to sloppy coding, overuse or misuse of long. For example, send message or post message API has wparam and lparam in it. And I remember going from Win16 to Win32, and the whole world was out there changing all those word casts to long casts. And I remember saying to programmers that were on projects I was running, hey guys, cast that to an lparam. It's an lparam. Cast it to what it really is. And my programmers would say, well, why? They're both 32 bits. Well, the why is here now, because lparam is now 64 bits. And if you coded lparam before, it just compiles and it just works. So use the data types that are explicit to the type of thing they refer to. When you're casting an lparam, cast it to lparam. When you're casting an H instance, cast it to H instance, instead of making an assumption that it's the same size as a long or anything else. Another one that I've seen most commonly is people that said, well, I'm testing for -1 and I know which bit that is. So I'll just say 0x and a bunch of F's to mean -1. Well, if you use that exact expression with that number of Fs and you're testing a 64-bit value, it doesn't work. So you'll find a lot of code with a 0x that's not going to work, and you got to change that to a -1 in the source code. We'll see one of those later. Another danger area is 32-bit, 64-bit cross-process that's not marshaled. If you're doing RPC, or you're making COM-based calls cross-process, in general, that stuff just works because you've got a marshaller involved that's unpacking your structures and serializing it and then repacking on the other side. And that pack and unpack deals with the size differences in your data structures. But if you're doing shared memory access or you're sharing a structure on disk, that's where you need to be careful because the structure sizes changed if there's anything in them that was 32 that went 64. Or the structure sizes change because the packing is different. Itanium wants 8-byte alignment. So your default packing is going to push things out to their natural boundary, which will be 8 bytes for a 64-bit entity. So another one to watch out for. Code which uses the high order address bit. Bad practice, which unfortunately, I bet some of you have code. You didn't do it, I know. But the programmer that wrote the code that you inherited might have done that. You know, bit 1 is never used, right? It's just really 2 gigabytes I have. It's just 31 bits in my addresses, so I'll use that for a flag. Well, when we go to 64-bit pointers, bit 31, the 32nd bit, becomes just a regular old real bit that's part of a 64-bit or 63-bit address. So that's a piece of code to go look for that the compiler is not going to find. Pointer truncations, a cast that chops off the top 32 bits of an address is a gotcha. Where you also have a problem is when you have a pointer that's a return from a function call. I've got a little sample here. The function call is okay, but the piece of data in the structure where the pointer's being stuffed, I've only got 32 bits in the structure. So I call this function, he gives me a pointer, stuffs it in some memory location where I've only set aside 32 bits. So that's another piece to look at where you need to look yourself. And I've already mentioned structures stored on disk, where that structure is exchanged with 32-bit processes. And in particular, look at the pointer-derived types that you might have used in there. I mentioned alignment. I said he wants 8-byte alignment. Here is an example of some good and bad code that works or doesn't work based on that. You see in the wrong, I have a structure here that starts with a D word and is followed then by an array of pointers, my foo structure. In the wrong code, I say malloc, size of D word, plus 100 pointers. That works fine on Win32, and that breaks on Win64 because those pointers are going to be 8 bytes aligned. So in a Win64 compile, for that D word number of pointers, 8 bytes are going to be set aside. The offset of the first pointer is plus 8. So really I need 100 times the size of a pointer plus 8, not plus 4. So the correct thing to do is malloc for the offset of the pointer array. The offset of macro is going to return a 4 on Win32 because the pointer started plus 4. It's going to return an 8 on Win64 because the padding caused that offset to be at plus 8. So with the correct code, I'm going to allocate 100 times pointers plus 8. The other ones the compilers don't get is references to polymorphic data. You can have implicit or explicit polymorphic data. You can have real unions that you've explicitly coded, or you can just know in your code that certain data sitting in memory is sometimes one thing and sometimes another kind of thing. So that's an area of the code as you're reviewing the code to look at and to think about. A gotcha that I'll get to in a minute is going to be about COM objects running in process. You can't mix bitness on 64-bit Windows. You cannot have a Win32 DLL calling a Win6Xe or DLL calling a 64-bit DLL or vice versa. What that'll mean in practice is you can't put 32-bit DLLs into your 64-bit process, and since in-process COM servers are DLLs, that means you can't use 32-bit in-process COM servers. So one way out of that is to run those in-process COM servers out of process, for example, with an Xe named DLL host, which, if performance allows it, is a solution if you can't get a 64-bit version of that in-proc server. And the showstopper gotcha is probably assembly code. The assembly for Itanium is called EPIC. That's Intel's acronym for the assembler language, the instruction set of an Itanium processor. And it's not x86. It's nothing like x86. And in my opinion, if you've got any assembler code today for x86, you want to rewrite that in C code. You probably don't want to learn EPIC Itanium assembler. It's very complex. The benefit of this processor is not in the clock rate. It's not because it's a 5 gigahertz or anything processor. It's because of the way it handles and the way it pipelines and processes instructions and the way it does parallel execution. And you need to know all those things in the assembler you write, and that makes the assembler complex to write. The challenge for us really in getting 64-bit Windows together has fallen on the compiler team that can take the existing C code and make good EPIC code out of it. How many in the room have a device driver? Anybody? You must create a 64-bit version of your device driver. Device drivers must be 64-bit code. There's no support for 32-bit device drivers. The drivers follow the same safety rules as for Windows 2000, and you need the same code signing, etc., as in Windows 2000, and they need to be plug and play as in Windows 2000, because this is 64-bit Windows 2000. Complexity, and that can be straightforward. That can be completely straightforward to create a 64-bit driver. Where you get some complexity is if your 64-bit driver needs to be called from both 64-bit and 32-bit address spaces. And in that case, your driver needs to export 2 sets of callable interfaces, which are called I/O controls, I think, in driver space. I'm not a driver guy. And you need to be cognizant of which interface you're being called on, and you need to deal with data sizes, because they'll come in 32-bit from the 32-bit process. Rapid migration for the really bad code out there. Suppose you want to be IA64. You want to get that EPIC instruction set. You want to get that speed potential that is offered by Itanium. But a 2 gig address space is okay. There's plenty of space. The nature of your app is such that you never need anywhere near even a gigabyte of address space. And let's suppose that code has lots of pointer truncations and lots of warnings out of the compiler, and you're just mixing ints and longs and pointers all over the place. It would be a massive amount of work to make that clean code. For that class of application, there is an alternative in 64-bit Windows, which we, by nickname, call the address space sandbox, which can be a good place to run this bad code and still let it be EPIC Itanium assembler code. Technically, what this is a flag on the executable, which, if set, tells Windows to never do an allocation above the 2 gigabyte line. So if this flag is set, whenever you allocate memory, what you're going to be given back is a 64-bit pointer where the top 32 bits are always zeros, which means you can freely truncate, throw away, change that top 32 bits, later extend it with zeros and pass it back into Windows, and everything will work. So here's some code you can take a second to read, which shows exactly that. Here I do a malloc, a memory allocation, and I put the pointer into a variable called source, which is a 64-bit pointer to a void. Here I assign the value in source to DW, which is only a D word, which is only 32 bits. So in the act of this cast, I have thrown away the top 32 bits of that pointer. If this was a regular old 64-bit XE, I would have just thrown away real address bits. So I would now have a bad address. But because I'm in the sandbox, those bits were zeros. And so I can now take, where'd my pointer go? I can now take that D word, do an assignment back to a p-void variable, dest in this example, get extended with a bunch of zeros, and when I do that assert there, it asserts true. Because the pointer that came in had zeros, I can put the zeros back. What's the gotcha with this? The gotcha is that the OS only checks this flag at create process time. It only checks this flag when it loads the XE. So if you start mixing and you put a not aware DLL in an aware XE address space, you're going to start trashing the pointers of your parent process. Not parent process, your parent XE that called you. So this works fine if you've got an XE and that XE is pretty self-contained, or an XE and a few DLLs that are self-contained, where the whole set is either large address space aware or not. This doesn't work if you're making a DLL that you sell commercially. Because guys that run your DLL in a real 64-bit addressing address space, you will cause corruption of their pointers. I mentioned that an address space is either 64 bits or 32 bits. So you cannot mix 32 and 64-bit in an address space. All the DLLs, all the in-proc servers must be 64-bit. A Win64 process works just like you're used to Windows 2000 working now, where the 64-bit process has all this code running in user mode, and when it makes a kernel API call, we switch into kernel mode. In the 32-bit process, what we've done is we've actually shipped a copy of 32-bit Windows 2000 kernel, user, and GDI. And those run in your 32-bit address space. So when your code makes a your Win32 code makes a Win32 call, you actually go into kernel, user, or GDI 32 running in your address space. So we're not thunking at the Win32 API level. We're not going through that conversion of pointers to 64-bitness and back. So that's a straight, clean, no extra overhead kind of call. It's the kernel level APIs that go through the thunk. So when kernel 32, GDI 32, et cetera, makes the kernel call to go into kernel mode, that's where you go through the boundary from being in 32-bit mode, x86 instructions, to 64-bit mode, epic instructions. That's the thunk, as we call it, where things get expanded to 64 bits going in and truncated to 32 coming out. That's good because those calls happen much less frequently. That's good because there's a lot less code making those calls. And there's only a couple of hundred of them instead of a couple of thousand. So our scope of effort to write the thunking code was much less. There's not very many user apps that call those APIs. That also gives us good compatibility because you're running the same kernel, GDI, and user 32 that you run on Windows 2000. So how do you get to 64-bit Windows? How do you move your code there? Early hardware developer bits were distributed by Intel. And in 1998, Intel shipped an Intel SDK for Itanium with an IA64 simulator, they called it, where you could actually simulate the Itanium stuff on a Pentium box, which was fine for apps that had resource demands like Notepad does. It was slow. Later in 99, quite late, Intel started shipping machines. And you might hear somebody say the term SDV, which stands for Software Development Vehicle. And so that's what Intel calls an Itanium computer. And there was a very serious NDA required to be signed with Intel, et cetera, to get these machines. And they were targeted at companies that write operating systems like Microsoft and companies that make and sell computers like Compaq and IBM and Dell and NEC and NCR, et cetera. The next step will be the start of a Microsoft beta program for 64-bit Windows. The Microsoft Platform SDK that ships today has in it the documentation, the header file, and a phase 1 compiler to work on clean code. The one that ships with the beta that will ship by the end of the month will also include the linker and the debugger. So you can actually create executables for an Itanium computer. And then 64-bit Windows 2000 will ship when those computers ship. So when the Compaq, the Dell, et cetera, when the computer companies ship computers with Itanium processors, Windows 2000 64-bit will be pre-installed on those computers. And then we'll have a formal release of 64-bit Windows after we have the time, a month or a few, to do a full quality assurance on the actual released hardware. Next step here in the talk is to look at the tools to build 64-bit Windows apps. Visual Studio is what most developers are using today to build Windows code. And we're working now on a next major release of Visual Studio, which is currently referred to as Visual Studio 7, although by the time it's released to market, it may or may not be called Visual Studio 7. It's 32-bit focused on enterprise and web development with lots of good stuff in it. That's part of the evolution of both Visual Studio and the evolution of the computing paradigm from the desktop and client server into web-based development. After Visual Studio 7 is released, there will be a follow-on, which is a 64-bit version of Visual Studio, which will be the same as the above, but ported and tuned for Itanium development. So we'll have the same feature set for 64-bit Windows that we do for 32-bit Windows. And when Intel released those SDVs, Intel also released a platform SDK, which had a lot of Intel technology in it, Intel documentation, Intel compilers, et cetera. Well, back in 1999, during the Windows 2000 beta program, the Windows 2000 Platform SDK started to contain 64-bit headers and compilers. How many of you have seen that? How many of you have noticed that how many of you installed the Platform SDK? Well, I would say that's 15% maybe. How many of those have noticed that there's 64-bitness in that SDK? That's significant. That's most of you that install it. It's there. Everything I've said about types and base TSD, a bunch of words about how to move your code to 64-bit are in the documentation that's been in the Platform SDK since Beta 2 of Windows 2000. And these are Pentium-hosted tools, so you can get going now with using those tools to get your code to the clean compile stage before you have access to a Pentium computer. Then when the beta ships, as I said, we will have, in addition to the Microsoft compiler, a linker and a debugger. And then later, the final step will be full Visual Studio 64-bit. The compiler and linker that are shipping in the SDK are from the Visual Studio team. It's the same compiler, but you don't have the full studio and the tools around it. You've got a command line, CL, C1, etc. exes. The tools are focused first on being robust and being correct. The compiler that we're offering to you is being used to compile Windows NT, to compile SQL Server, etc. So we've compiled jillions and jillions of lines of code, and this is being done with a parallel development team that makes a code generator that generates this epic assembler. There are lots of optimizations that are part of life for Itanium assembly lever code. There are a lot of tricks from a software guy's point of view that you use in order to generate a code that is much more efficient on an Itanium. Now, I've had a lot of experience where I've played with the compiler switches that said optimize for speed, optimize for size, don't optimize, do a debug build. And in a lot of code I've done that, I see pretty subtle change or small change, almost immeasurable change sometimes. With Itanium, it's going to make a big difference. This is a list of the kinds of optimizations that will apply to code for Itanium on 64-bit Windows. So these are the kinds of optimizations that are built into that compiler. What the compiler guys want me to say that they're focused on integer and real-world code performance, not building a compiler which is a spec warrior that just gets great results on benchmarks and in the real world may or may not produce good code. Out of all of the optimizations that are available, one that's a new idea for some will be profile guided optimization. The idea here being to know which path the code is going to take when it does most of its execution. So in the top row there, you see a compile step where you take the source code and you compile in a manner that inserts instrumentation code into the produced objects. So you end up with instrumented object code. What you need to do then is run your tests, run this instrumented object code with representative input data. Representative of the way you expect this app to be used in the real world. So you take the code paths during this test so that you take the code paths that will be most commonly taken in production. And out of this instrumented run, you get some profile data. You then recompile with your original source code and now this profile data to produce optimized object code. This will be making a large difference in the performance of your code. This is something you must plan to do with your Itanium targeted code. And maybe not for your incidental apps, but for your mainline code, plan to do this. Make sure you do this. It's critical for best performance on Itanium. So before we go to resources and call to action, let's go look at an Itanium. Did they both come up? This is Windows 2000, 64-bit, running on an Itanium computer. And if you look to the bottom right of the screen, you will see it's Windows 2000 Advanced Server, 64-bit edition, and then the build number. So this is the current build that we're using internally as a self-hosting build for internal test and ongoing development. Over here in the system properties, you see this is an IA64 SDV. That's the software development vehicle. And you'll see that it has 0.98 gigabytes of RAM. Over here in Task Manager, you can see from looking at the CPU time used by the system idle process that it's been up for a while. Now that's the task man you're familiar with. This is the system properties that you're familiar with. This is a desktop that you're familiar with. While at the hardware architecture level, this is a whole new ballgame for 64-bitness. While IA64 as a machine architecture is a whole new ballgame, to the user, it's Windows 2000. To the system administrator, it's Windows 2000. Therefore, the cost of deployment, the cost of ownership will be not any different, really, than owning one more Pentium box. If your systems administrators know how to configure, set up, do networking, etc., on a Windows 2000 Pentium box, they're already trained to do it for an Itanium box. So it's a fast, easy, just one more Windows 2000 machine deployment. Same thing for end users. It's all the same. So there's sameness preserved for usage with the benefit of higher scalability, higher performance, larger apps, etc., with straightforward change at your code to go Win64. This machine that I'm showing you right now is in Redmond, Washington. A feature of Windows 2000 is terminal services. A feature of Windows 2000 is virtual private networking. So what I've done here with my laptop is make a VPN connection to a little network we have in Redmond with a bunch of Itanium boxes on it. And so Barney here is in Redmond, and this is a terminal services session on Barney. If I Alt-Tab, you'll see a bunch of processes running here, which are all running right here on this laptop. It's only that process which is Barney. If you go into the SDK, oops, I missed it here, sorry. If you install the Platform SDK, you end up with an entry called Microsoft Platform SDK. Those of you that are Visual Studio users and don't install the Platform SDK, I strongly encourage you to do it. The Visual Studio the SDK comes from the Windows 2000 team. So the systems guys put out the SDK. There's documentation in there, there are samples in there, which Visual Studio doesn't ship. The Visual Studio team is a product. They're competitive in the marketplace. They pick and choose the pieces they think are right for their product, and they don't pick everything. So you're missing some good doc and missing some good samples if you don't look at the SDK. The SDK today has a bunch of doc which is in HTML format, and it also has documentation which is text files. And notice this one is README 64. And README 64, I'm not going to read it, but I'll make it bigger. README 64 has in it the set of instructions you need to follow to set your Windows 2000 box up to do 64-bit development. Instead of taking the time to read that through, which you can do on your own, let's just take a peek at what I've set up. This is Visual Studio 6. This is plain old VC6 running on Windows 2000 on a Pentium machine. But what I've got in here is two projects. I've got a normal pviewer project, pviewer being one of the samples in the SDK. And I've put up a second project which has in it an external build. If we look at the project settings, you'll see that the build for this, instead of being a normal Visual Studio, all it knows about the build is simply a command line that, in my case, executes a command file named build64. So I take pviewer, set up a normal Visual Studio project, I build pviewer Win32, make sure all that's good first. Then I set up an external project which simply executes this external command file. And here is that command file. And I have an echo just to tell me it's running. And then I call set win64.cmd. That's a command file that sets my environment. That's a command file that comes with the SDK. So it sets the path, it sets environment variables, etc., so that down here, when I say make, that make is going to find the compiler, that's the 64-bit compiler. It's going to find the libs and the headers that belong to the 64-bit build. So when I run this make, it's going to go find makefile.nothing, and that is going to build a 64-bit executable. And as you see below, I just did that here, and I got a nice build with 0 warnings. And if we look over here in my code directory, there's code, there's pviewer. There's pviewer.exe. So this is the exe, which is the output of that build. Let's run it. Well, it won't run. Why won't it run? It won't run because it's a 64-bit exe. The format of the file is called PE32+. It's like a PE32 format executable in its general structure, but it's marked to say, hey, this is IA64 code. Needs to run on an Itanium. So we'll go back to Barney. And I've copied that file up here to Barney. And now we have process viewer, or pviewer.exe, 64-bit, running on an Itanium box up in Redmond. Now, was this just a clean build? No, it was not just a clean build. pviewer, in fact, breaks all the rules that I mentioned in the slideware. So I've got WinDiff up here, and on the left side, I've got clean pviewer that builds 32 and 64. And on the right side, I've got pviewer original that's shipped in the Win32 platform SDK. So let's walk through and look at the differences. So here I have a function call, pview dialog change priority. It has 3 arguments. Notice the second argument is now typed as a W-param. And in the original code in yellow, it was typed as a D word. So there was one of those assumptions that W-param would be 32 bits the size of a D word forever. So I had to change that from D word to W-param. Set class long. I don't think I mentioned earlier in the talk that there are a few functions which have had name changes, and this is an example, set class long to set class long pointer, because they're dealing with 64-bit instead of 32-bit entities in a polymorphic manner. So if you do set class long pointer in your code, it's going to compile write 32-bit and 64-bit. And notice the types here, the second one, I've had to make that a long underscore pointer, so it compiles both ways, 32 or 64. Another LParam. Another time the programmer said, oh, long, that's good enough for an HWin, instead of typing it to an LParam or typing it to an HWin. Send message. This is a send message to a dialog box, a list box, I mean. And it's returning information about the entries in the list box. And it's assigning that to a D word. Instead of changing the DW process index variable, which takes the return value, to a 64-bit integer, where is it? It's up here somewhere. There, I have a D word variable that's taking the return from this send message. And the send message is now returning 64 bits. So I could have changed this up here to become a 64-bit variable, but instead, I decided to explicitly cast the return to 32 bits. I decided to chop off those top 32 bits and throw them away. Why did I do that? I don't think my list box is ever going to have more than 4 billion entries. Now, I could argue this case either way. I could argue that, well, this is an assumption. Who knows how big the list box might be in the future? You know, in the 70s, we all said, well, this code's never going to be running 30 years from now. I don't need more than 2 digits for my date. So I suppose this code might be running in 1,000 years, and we might have more than 4 billion in a list box. But I wanted to illustrate the point that you don't want everything always to go 64 bits. Because if you allocate 8 bytes for thousands of variables and you never count to more than 100 in them, there's 7 bytes laying around doing nothing. So there are cases where it's probably smart to leave the variables as 32-bit variables and explicitly truncate them down, as I did with this dword cast. Same thing here again. This is another send message to the list box. This now is that function. The first change we saw was a change to the prototype for this function. This is now the function that said dword for what was in fact a W-param and had to be changed to a 64-bit type. First one there is another send message. Same issue again. I decided in this case to leave the variable 32 bits and do an explicit truncation or type. Another send message. And then the one I like the best, the if DW index equals 0x and 8 foxes. Test for -1. So you got to be -1, or you've got to use the types, the OK error types that are defined in the Windows header files. A couple more send messages, and you're starting to see some repetitiveness, right? Repetitiveness. It's the same error that's occurring multiple times because the programmer had a way of coding. Another send message, another send message, another send message, another send message. No more changes. So the point to take away here is that there's only a few kinds of things that had to change, and one of them, 2/3 of the changes in this program were actually the same kind of change to the send message that was assuming a 32-bit return value. Okay. Where do you go for more documentation? Go to the Platform SDK. Or if the Platform SDK isn't there, if that CD is not there for you, go up to msdn.microsoft.com and search on Win64. When you search on Win64, you're going to get about 10 hits, and I think it's the second hit. Click, click. And it'll take you into the documentation about 64-bit development, the same documentation that's in the Platform SDK. And the getting ready is the right general purpose place to start that talks about the same issues that were the body of this talk. I mentioned that 32-bit DLLs won't work in 64-bit processes. I mentioned that 32-bit in-proc servers won't work. There's a lot of third-party code out there that people use. There's probably a lot of third-party code that all of you use. So when you start moving to 64 bits, you might find some dependency. You might say, I can't get there because XYZ from Foo Software has to get there and I need it. We need to know about that. So please send email to drgwin64@microsoft.com about third-party code you depend on. And if you tell us who those people are, we will contact those people and we'll invite them to come to 64-bit Windows. And we'll help them get there in support of your development. What you should do is start with good code for Windows 2000 and then make that code 64-bit ready. You should know what's in that readme64.txt file in the SDK. You should start using base tsd.h and using the types and functions that are in there so you can get 64-bit ready now on Windows 2000 on your Pentium computer. And you can do that today with the compiler and the types at the clean compile stage. And in a month or so when the beta is running, you can go all the way out to an exe and a debugger with the tools that are in the SDK. At that point, you're going to need an Itanium computer. And what you need to do now is go to your hardware vendor, whoever that might be, Dell, Compaq, NCR, NEC, whoever that might be, and tell them you're doing 64-bit work and you're going to want a computer. If you've got Intel contacts, tell them. And if you need a machine and those things aren't working, tell me. And I will help you get a machine, or I will give you access to that machine in Redmond that I was running here in the demo, so you can do your work remotely. And I showed you that remote demo for two reasons. One, to show you that it was there available for you to use from Redmond. And also because even if you do get some Pentium machines, there's probably going to be less Itanium machines. You'll probably have fewer of them than you have developers. So you'll probably need to share those machines even if you get one or a few in-house. Terminal services is the most excellent way to do that. You can either send email to me as stanmu@microsoft.com or to that DRG Win64 alias, which will work better if I happen to get run over by a bus or anything like that. Now, after you've got clean code for 64-bit Windows, you want to then think through taking explicit advantage of 64-bitness. So this is my exploitation call to action. Think about what you can do with a large integer. Think about if you've got algorithms now that know that they're going to count past 2 billion or 4 billion and are dealing with multiple registers and multiple integers and overflow. Think about if you're doing something in floating point today that might run a lot faster if implemented as an integer arithmetic algorithm, which maybe you can do now. Even if you're counting lira, you can now count those lira in an integer and still get up to the kinds of dollars involved in buying A300s. Think about what you can do with large memory. My best example was that video editing application, where with the Win32, Win64 file mapping, you can now map huge entities in the memory. And as long as you're only hitting spots in that video, you're just doing minute 3 and minute 72, there's not a big performance issue because you're not ripping through the whole stream. So you also need gigs and gigs and gigs of RAM. If you want to get in the beta, beta rec at Microsoft.com is a general alias run by the Windows beta team. And that alias is intended for you to request entry into any beta program that you know about on any Microsoft technology. So it's not limited to just 64-bit Windows, but that team is right now finalizing and developing the list for 64-bit Windows. If you want to get into the remote lab that I was demoing here, then DRG Win64 is the alias to mail and ask for entrance to that lab. And then Microsoft.com, MSDN, is always your primary resource. And if you've got commercial applications and you want to get involved in some marketing programs, be sure to look at partnering at msdn.microsoft.com. So we'll have some little music here. So anybody that doesn't get it about the theme here with When I'm 64, you will love Windows even more when she's 64. If anybody has questions, please come to the microphones.
You mentioned that the platform SDK had been, it had the 64-bit header files for about 2 years now. Any plans on making the platform SDK 64-bit clean as well?
Any plans to make it clean, is that what you said?
64-bit clean?
Yes. We have an active there's an active project inside Microsoft now to take all of the samples and make them 64-bit clean, except for a few that might just be, for some reason, legacy. And that brings up a point I'd like to make about the SDK in general. We feel that we've not invested enough in the SDK over the last few years and have beefed up that team considerably just in the last few months and intend to make the SDK a shiny jewel once again.
2 questions. First one is you listed SQL Server and Exchange as being the first apps that are going to get ported to 64 bits. Once that happens, does that mean that we will have to run SQL Exchange on an Itanium?
No, there will be, it's parallel. There will be SQL Server 32 and Exchange 32 for the foreseeable future, just as Intel will be selling high-end Pentium chips for the foreseeable future. Those people that want the next plateau of scalability and choose to go Itanium will have a 64-bit SQL and Exchange to run there.
Okay, next question is, you mentioned about making no assumptions about the size of pointer, checking the range of values and such. Now, I've seen in the header files, like limits.h, that you have maxint, 64, maxint 128, but I don't recall seeing anything that's abstracted or generic where you can just say maxint pointer. Is there something like that that will determine the maximum range based on the hardware?
I think your question is there a macro, a max type macro that will give you the maximum for this current compile? I think, I'm not sure here, I'm guessing a little, but I think max int is going to be 4 billion if you're doing a Win32 compiler and 16 or 8 trillion if you're compiling with the Win64 compiler. I think it goes polymorphic. Is Kyle in the room? Maybe I can get a more specific answer if you find me at the booth,
okay.
The 64-bit booth at the trade show this afternoon, or at Ask the Experts tomorrow.
Good.
I'll try to get that one.
You mentioned that integers are still 32-bit under Win64. So I'm not quite sure, and maybe this is just my ignorance, why hex FFFFF is not equal to -1 anymore. Why would it be sign extended?
I said that integers were still 32-bit. To be more explicit, the type int compiles to a 32-bit entity.
But is, like in the example for PViewer, you had a D word, so is D word still 32 bits?
D word also, just as the type D word and the type int both by default, are not by default, both do compile to 32-bit entities. If you want a 64-bit integer, you must use an explicit 64-bit type, such as int64.
Right. So it seems like maybe that example would have worked the way it was coded.
I'll take a look at that sample, make sure I've got an accurate example in my slideware.
All right, thanks. Right. Okay, I see.
2 questions. You talked a lot about the pure 64-bit integer, which is very nice. But back in the 3.1 days, your floating points went out to 10 to the 44,900th power. It dropped down to 10 to the 308 with NT because you were going to multiple CPUs. Is that going to extend back out, or what is the new limit for the floating points, especially the long double types under the 64-bit NT?
I'm not expert on floating point. The answer I'm able to give is that I believe the precision of the floating point unit in Itanium is the same as on Pentium, but I'm not 100% sure that's a right answer. I will also try to get an answer to that by Ask the Experts if you want to come by, or you can send me some email on that, or maybe the hardware guys at the trade show know. There's NEC guys with the NEC Itanium box in our booth.
Okay.
And Compaq at least has an Itanium on the floor as well. I think 80 bits is a precision on Pentium. Yeah.
We're currently working on porting our code to 64-bit, and I run into a problem with the bin place utility. When we compile under NT4, it compiles okay, but the bin place utility doesn't work. It works fine on Windows 2000, but you know, we compile our code for 4.0 and 2000 on 4, but it looks like we're going to have to compile, you know, the 64-bit on 2000 and the rest of our stuff on NT4.
Yeah, don't know the answer. That's a good product support question. I encourage you to ask for entrance to the lab or the beta program, and that will get you into the support news groups. That's a really excellent PSS question.
Okay, thank you.
Currently with NT, there's only 4 gig of memory that you can address with an application, and it's split for, unless it's enterprise, 2 gig and 2 gig, and then if you go to...
Right, the address space on Win32 is a 4 gigabyte address space, and 2 gigabytes are for the application, and 2 gigabytes are for the system, except with NT Enterprise, where the application gets 3 gigabytes.
Right. How does that change
It
with...
becomes 16 terabytes instead of 4 gigabytes.
But is it still...
8 terabytes for the system, and 8 terabytes minus 4 gigs for the user. Because the bottom 4 gigs are reserved for the Win32 processes. So you get 8,184 gigabytes.
But it's always a 50-50 split.
Yes, it's a fixed split.
Okay.
Now, will there be a 64-bit Windows NT Enterprise down the road somewhere? Maybe. No plans.
No plans for that?
We think 8 terabytes is big. The other thing that's true, if you think the math through, we aren't using all 64 bits right now. That's not 2 to the 64, it's 2 to the 54, I think. And that's because if you support all 64 bits of addressability, the page tables, to keep track of the pages, become huge. And that would be too much overhead for the size of RAM that we're running today. So we've got growth to make the 16 terabytes bigger.
No, the concern I have, though, is just like they did with Enterprise, they took a gig out of kernel and put it into user to give some of these applications that require tons and tons of memory a way to do that, and didn't have that adverse effect on the kernel side of thing. And let's say you had an application that needed 4 terabytes, you need to buy 8 terabytes when the operating system probably could get away with just using 1, or the kernel at least I should say, 1 terabyte of space. You're wasting 3 terabytes of RAM for all intents and purposes.
Well, it's 3 terabytes of virtual, though. It's not RAM. Right. Most of the apps that broke making the move were apps that used that high order address bit as a flag. Because when you go up to the 3 gig line on NT Enterprise, then that top bit might be real. So that's the only thing that's a main general thing to make sure you don't do if you want your code to be able to move up later. So just don't use those top bits.
This may be mostly a compiler problem or question, but what's going to happen to the lowercase int and long and double and all those kinds of types?
Oh, you're right. Those choices are built into the compiler, and the compiler vendor chooses which way they go, and we've chosen that they go 32. And if you read base.tsd.h, you'll see all those derivations. And by the way, if you use the Windows.h that's in the Platform SDK, it automatically includes base.tsd.h. It's one of those implicitly included files. Thank you very much, and be sure to turn in your evals.